Okay, today we're going to talk about the dreaded Chapter 8, disorders of fluid, electrolyte, and acid-base balance. Now remember, I want you to keep a high-level overview, and I may go into a little bit of detail here, but really we're going to focus on just a few fluids and electrolytes. So the main goal for the body is that all body functions maintain this homeostasis that allows the body to function at its highest level. There are three main areas that do this. That would be the brainstem or the medulla oblongata, and that mainly controls respiration and circulation. You have the pituitary gland, which we call the master gland, and this gland controls growth, maturation, and reproduction. And then we have the reticular formation, where nerve cells control all the vital reflexes. Homeostasis feedback mechanisms work through a few different mechanisms within the body. We have sensors that are self-regulating, and there are feedback mechanisms throughout the body that identify disruption down at a cellular level. We have a main control center, which regulates the total body response. So basically this main control center is the part of the body that's in charge. And then we have effector mechanisms or hormones that either negatively or positively act to restore homeostasis. In negative feedback mechanisms, you need to understand that it gives you a positive result. So in a negative feedback mechanism such as glucose monitoring, the body at the cellular level senses that there are high glucose levels, which in turn causes a signal to be sent, a hormone to be sent to increase insulin production in the pancreas so that we can get that glucose level back down to a normal level and maintain homeostasis. So keeping that in mind, a positive feedback mechanism means that it proceeds in the same direction as the change. It takes that original response and exaggerates it, and some of the things, generally we don't like positive feedback mechanisms. Off the top of my head, I can think of chronic diseases that create this kind of a feedback mechanism. One of our normal physiologic changes that works in a positive feedback mechanism way would be when the body's in labor, when a mother is in labor, there's a secretion of oxytocin, the hormone, that creates the cramping or the labor contractions. And the more oxytocin that the body senses, the more it sends, because the job that it's trying to do to get us back to homeostasis is to get that baby out, and then the oxytocin hormones drop, and then the contractions stop. So a positive feedback mechanism means that it's going to create more of whatever the change is that's occurring in the body. All right, so that's a big high-level overview of the things I want you to remember. Keep in mind that positive and negative feedback mechanisms, you may be asked whether something is positive or negative, and so that would demonstrate that you understood those concepts. In your PrepU quizzes, before the test, we will have some questions like that so that you can get used to what might be asked. Now let's talk a little bit about fluid distribution and the high-level overview that you need to know. So basically the fluid in the body is comprised in two different spaces we call the intracellular compartment and the extracellular compartment. In the intracellular compartment, that's where 40% of our body weight is contained, and the electrolytes that are kept there or that are harbored in that intracellular compartment are basically potassium and a little magnesium. In the extracellular compartment, now remember this is 20% of the body's weight, this is where the plasma and interstitial fluids reside. The big electrolytes that are in these compartments, think sodium and chloride. Plasma makes up about 5% of this compartment. Gases, nutrients, waste from the vascular compartment to the cells and to act as a reservoir to give capacity in case of substantial blood loss. Fluid moves in and out of capillaries, largely driven by the movement or the positioning of sodium and chloride in the body. We know this, or we talk about this in terms of serum osmolarity. So the tonicity, whether it's hypertonic or hypotonic, influences that movement of water across the cell membrane. We're not going to get into a lot of the details in that, but keep in mind that hypertonic solutions cause our cells to shrink, and hypotonic solutions cause our cells to swell. Normal saline or 0.9 saline is considered isotonic and is the fluid that most closely matches the fluid within our bodies so that it maintains cell activity and cell water at the optimal level that's needed. When we talk about edema, and this is the swelling that you see that occurs in interstitial fluids that produces the visible sign and symptom that we see as edema, we know that there are pressure forces we know that when edema is present, there are pressure forces that are assisting forcing that fluid into interstitial spaces. And this is just a nice picture of what that looks like. Just a quiz for you. And the answer to the quiz. So let's get into the nitty-gritty. You will have to remember the normal ranges and pretty much commit these to memory. As you get into hospital systems, there may be some slight variation as to what their normal ranges are, but for the most part we try and standardize this, so you will have to memorize these. Normal level of sodium is 135 to 145 milliequivalents per liter. Sodium is considered the big regulator of water balance within the body. 95% of osmotic activity occurs in the extracellular fluid, and sodium loss generally occurs in the kidney, and there are multiple mechanisms that take place to regulate the resorption of sodium in the glomerulus, and if you have disease in that area, these processes to regulate water balance become ineffective, and thus creating several other signs and symptoms and disease processes that we see. Sodium loss can also take place through the skin and the GI tract, but that's only about 10% of sodium loss. So the main purpose of sodium in your body is to maintain an effective circulating volume. So think of sodium as the regulator for arterial blood volume or blood pressure as we know it. That's probably the biggest thing that you need to know about sodium. So where sodium is, water will follow, and it helps keep our blood volumes at a level that can manage, that can help the body. If you have high osmolarity, I hate the word. If you have high osmolarity, this creates a situation where you become thirsty, and it sparks the body to seek out the need to take in water. It also sparks the release of a hormone, ADH, antidiuretic hormone, which increases water resorption from the urine. The opposite takes place if you have a low osmolarity, you have a decreased water intake and a lack of thirst, and a decrease in your antidiuretic hormone release. Based on what we just talked about, the answer to this question is true. Antidiuretic hormone prevents diuresis by causing more water to be absorbed in the tubules. Which leads to what we see as a decreased urine output. Dehydration due to lack of drinking, hypodipsia or lack of thirst, is a common problem in elderly people. There are many antidiuretic hormone imbalances. The biggest one that we will see is diabetes insipidus. You do not have to memorize this for the test, but you do need to understand that diabetes insipidus is related to an imbalance in antidiuretic hormone. We won't be testing it, but you'll go into this further in detail in Nursing 250. When we see patients with sodium imbalances, either too much or too little, as you can see here, we tend to treat their imbalance by choosing a type of IV fluid to help with the movement of water and to get the homeostasis restored. Isotonic fluid volume deficit and excess are discussed in detail on page 173, table 8-3 in the 3rd edition. And there are also tables on hyponatremia and hypernatremia, signs and symptoms, and overall effects on the body that you should look at. And this will be something that you do have to remember for testing. Potassium is our next big electrolyte, important electrolyte in the body. Some say the most important electrolyte that we have. 98% of potassium is contained within the cells, and this is important to understand. Here is the normal level, 3.5 to 5.0. Potassium is a key player in the cell resting potential and is needed for the sodium-potassium pump to create different gradients between the cell membrane. It's also utilized to exchange hydrogen to maintain optimal blood pH. So big deal, but most of us understand that the big role that potassium plays is in the ability of is in maintenance of optimal cardiac functioning. Serious cardiac diseases take place when we have either too much potassium or too little potassium. Please review the table on table 8.5 on page 181 to see the signs and symptoms of hyper and hypokalemia. But know that its biggest influences are on the cardiac sector. So this would be one of those clinical things that you can review to understand. So if someone has one of these diseases clinically, what will happen to my blood potassium levels? Will they be too high or will they be too low? I will post the answers to this at a later time, but this is just something that you can help quiz yourself with in terms of clinical application so you understand what's going on. I put the basics of a cell fire, of how cells fire in here, just to review. This is physiology, so that you understand that sodium and potassium are highly interactive in the process, and so this explains why you see some of the signs and symptoms you do when you have too little potassium and too little sodium or too much. Calcium. After you've memorized sodium and potassium, calcium would be the next electrolyte that you needed to understand. You must know what normals are, and you must know that calcium is involved in nerve and muscle cell firing. It's also involved in clotting, and it acts as a secondary messenger in many hormone and neurotransmitter pathways. So, as you can see here, this indicates some of the ways that calcium is utilized within the body and the pathways that it affects and the hormones that deal with it. As we move further into our learning, we will come back and revisit how calcium impacts bone development or bone disease or kidney disease, and you'll get a better sense of what this picture means. But this is a good picture for you to understand all the different ways that calcium is involved in our body. Magnesium would be the last electrolyte that you can commit to memory. Do remember what the normal level is, 1.8 to 2.7. Magnesium's involved in a lot of the enzymatic reactions throughout the body, ATP production, DNA replication, and is integrated with calcium metabolism. So magnesium and calcium go together, and sodium and potassium go together. And you can kind of think of them as opposites. Again, calcium, the slide is out of order. I apologize for that. Calcium controls a lot of nerve cell firing, and so when I have too much calcium, my nerves are less able to fire. One of the traditional signs that we see when we have too little potassium is called Trousseau's sign. and it's an indication of hypertetany, and it's just a classic sign that you should keep in your mind. And I think the book has some pictures on that. If not, I can set some of those up for us. All right, fluid and electrolyte balance. Oh my God. Now we're going to get into acid-base balances, and I know that you covered this in your basic physiology class, but I think this is a really cool picture that shows you what the pH and so this is a great picture of what normal balance looks like when we're talking about acid-base balance in the body, and what it looks like when it's imbalanced. Again, as you know, I like pictures. In terms of acid-base balance, I don't want you to really freak out. My goal for you this semester is that you'll understand what true acid or base imbalance looks like, and you understand that there is a thing called compensation that the body does, but I won't be asking you to interpret any compensated blood gas values. Yeah, the blood gas values that you'll get on the test will be very straightforward and very simple, and my goal is that I can demonstrate that you actually understand the principles behind acid-base balance. So the acid in the body that we measure in acid-base balance is hydrogen. The normal value is a pH of 7.35 to 7.45. That would be what our body looks like when we're in homeostasis. Acid or hydrogen is highly related and controls the respiratory rate, and is also involved in different types of CO2 or carbonic acid is generally what gets increased when there is respiratory acidosis, and it lowers the pH and it increases the CO2, and it creates a system where the respiratory system is trying to compensate for the changes in the body. This is a nice graph that shows the difference between respiratory acidosis and respiratory alkalosis. It shows the changes that happen in the PCO2 as well as the hydrogen and bicarbonate. So those are the three elements that are utilized to try and bring the body back into homeostasis. And so when we talk about compensated, you may see that these numbers become very, very high, and the body has compensated for the increase in the acidosis. I think this is a really great picture that shows you how the buffering systems work in the body. And those buffering systems would be the systems that help try to bring the body back into homeostasis when it's out of balance. So buffering systems would be the kidneys, the respiratory system, and they will react in certain ways depending on whether it's a respiratory response or whether it's a metabolic response. So think renal is metabolic, respiratory is lungs. when you're talking about buffering for acid-base imbalances. Metabolic acidosis is an increase in some sort of acidity within the body, whether it be keto acids, whether it be lactic acid, and I would tell you that lactic acid is probably the biggest imbalance that occurs because of some of the anaerobic metabolism that takes place, which creates lactic acid when disease processes are in place. And metabolic alkalosis would be where you have increased hydrogen levels, and there's an increase in the bicarbonate levels to help balance those out. Again, a nice summary table for you to memorize. And that would be the end. I highly recommend that you go and do the YouTube videos that I've put up in terms of sodium and potassium, electrolyte balance, and there are some basic blood gas analysis problems that you can work your way through via YouTube, and there's a very simple system that someone has made up that I think makes it quite easy. So this ends our discussion of the dreaded Chapter 8. The chapter has way more material in there at a detail that I don't need you to know. Focus on your sodium and potassium, norms and abnorms, signs and symptoms, and basic acid-base imbalances in terms of respiratory or metabolic acidosis or alkalosis. Don't look at compensation, total